Greetings, traveler. I'm the Calculus Cleric, and today we're going to be going over applications of the integral in arc length. So the specific problem is to find the arc length of y equals e to the x over 0, comma a. Okay, so let's get started on this. So the formula for arc length using integrals is equal to the integral of b over a of the square root of 1 plus f prime of x squared dx. So we simply plug y equals e to the x. Oh, first we take the derivative, but we're just going to end up plugging e to the x in anyways. So y prime is equal to e to the x because the derivative of e to the x is just e to the x. And we take that arc length formula and then we can rewrite that. So that will equal, and our bounds are 0, comma a. So you take the higher number, which is clearly a in this case because it comes after the 0, 0a, and then square root of 1 plus e to the 2x, and then dx. I just squared the e to the x. And then from here, now what we'll have to do is take a u substitution of, believe it or not, the entire square root. And then du is equal to, we find the derivative of u, which is 1/2 of 1 plus e to the 2x, negative 1/2, because u can also be written like this. Because the square root can be written as 1/2. So what we're doing here is we're multiplying the front by 1/2 as the derivative rule states, and then we're subtracting 1, which gives us negative 1/2. And then now we have to take the chain rule of the inside part, which will get us 2e to the 2x. That's the derivative of e to the 2x, because what we're doing here is we're taking a shortcut of the chain rule. So the derivative of e to the x is just e to the x, and the derivative of 2x is 2. But you can remember that when working with e to the whatever x, whatever number's in front of the x just plops down in front of the e, and this part stays unchanged. And then don't forget the dx at the end of that. And then now we're going to have to flip everything over onto the other side so we can get dx is equal to something du. So multiply both sides by 2. So 2, and then multiply both sides by 1 plus e to the 2x to the half. Because that's a negative exponent, it's supposed to be a denominator, but because to cancel that on this side, we need to multiply it by itself, but as a numerator. And then we divide everything by 2e to the 2x to get rid of that. So then du is equal to dx. So this entire thing over here is equal to dx. We can cancel out the 2's here. And then on to the next phase. So what we can do here is there's a small little problem in which when we do a u substitution, we want everything to be a u, but as clearly we can see, we have x's on this side, which is a big no-no. But as we can see, u is equal to 1 plus e to the 2x the half, which is this right here. So we can replace that with u. And then the bottom part, we're going to have to figure out how to get that equal to, u. And so we just use algebra. One is u is equal to 1 plus e to the 2x. So we can square both sides to get rid of that square root, which gives us u squared is equal to 1 plus e to the 2x. And then we can subtract 1 from both sides, leaving us with u squared negative 1 is equal to e to the 2x. So e to the 2x is equal to u squared negative 1. We can plug this in over there. And that is our new dx. And then now we need to plug this back into the integral. Our integral was a0. And then we replace the square root of 1 plus e to the 2x That was our original integral, and then now a and 0, and we replace that with our u, and then now we need to replace the dx with our new substitution over there, u over u squared negative 1 du. And then we simplify that, giving us a 0 u squared over u squared negative 1 du. But we still can't do anything with this because we honestly don't know how to factor that out. And that's where partial fraction decomposition comes into play. And basically what we're going to do is with this guy is we're going to split him up into smaller fractions that equal this, but getting rid of those complicated degrees on the bottom so we can figure out what this is. But there's a small problem. We cannot actually use partial fraction decomposition in this case because the degree of the numerator is equal to the degree of the denominator. So u squared and u squared, the degree of the numerator has to be less than that of the denominator. So like u over u squared negative 1 or 1 over u squared negative 1. But we can make this into an occasion where the degree of the numerator is actually smaller than that of the denominator. And the way we do this is by adding a 1. So we just slap a 1 on the front, and u squared or negative 1 over u squared negative 1, that's equal to 1. The number on the top that will make this whole expression equal to just u squared is going to be 1, because u squared negative 1 plus 1 is just equal to u squared, as the negative 1 and the positive 1 will cancel each other out. And if we do it like this, now the rule for the partial fraction decomposition will be satisfied. The degree of the numerator is now less than that of the denominator. So coming over to here, we express it as a plus b over some numbers, which will be the factors of u squared negative 1. So we break this down. So u negative 1 and u plus 1 are the factors of u squared negative 1. So now we multiply both sides by u plus 1 and u negative 1, so that way we have no fractions. And let's just say I'm multiplying the same thing on this side. Very unorthodox, but I'm out of space. So this will just give us 1, because this multiplied back together is just u squared negative 1, which is equal to a multiplied by u plus 1 plus b multiplied by u negative 1, because when you multiply this by b, these two will cancel out. When you multiply this expression by a, this part will cancel out. But in any case, what I set the denominator of a and the denominator of b, it could be switched. So it's just arbitrary where you put each denominator, each factor that belongs in the denominator. It doesn't really matter about the order. You'll still end up getting the same things for a and b in the end. So to figure out a, we can set u to equal to some number that will cancel out b but leave a alone. And so we do this by setting u to 1. 1 minus 1 is 0 for b, and that gets rid of the variable b, leaving us with only a. So when we plug 1 into u, we'll get 1 is equal to 2a, 1 plus 1 is 2, and a is equal to 1/2 after divide both sides by 2. So we have our first coefficient. Now we set u equal to some number that will cancel out the variable a and leave only b. So let u equal to negative 1. That'll cancel out a but leave b alone. So 1 is equal to negative 2b, plugging in negative 1 into u. And so b is equal to 1/2 negative 1/2 after I divide both sides by negative 2. And so now we go back to the original expression, which is 1 over u squared negative 1 is equal to a over u negative 1 plus b over u plus 1. And then we replace a with 1/2 and b with negative 1/2, which will give us that 1 over u squared negative 1 is equal to 1 half u negative 1 plus 1. Oh, scratch the plus. It's negative 1 half multiplied by u plus 1 in the denominator. And so going back to our original integral, it was a 0, the integral of a 0 plus 1, and of 1 plus 1 over u squared negative 1 du. And what we're going to do is we're going to replace 1 over u squared negative 1 with this thing that we solved via partial fraction decomposition, and it'll make it much more easier to solve the integral itself. So substituting a 0 plus 1 plus 1 over 2 u negative 1 negative 1 2 u plus 1 du. And then now we solve the integral out, and that'll give us u a 0, because we got to go plug these things in after we solve the integral, plus 1 half ln of the absolute value u negative 1, because when we take the integral of, like, say 1 over x, we'll get ln absolute value of x. In all essence, we're doing the same thing here. We're just taking out the coefficient, putting it in front, as coefficients to some x do not matter when we take the integral. And then we're just treating u negative 1 as we would an x. And because there's nothing to really chain rule on the inside, we do not have to do any reverse chain ruling. And so we just do it like this. A good inequality to remember is that 1 over a of ln of ax plus b plus c is equal to the integral of 1 over ax plus b dx. So this thing, when we take the integral of 1 over ax plus b, b is just some random constant, so is a. And then, because we're taking the general with no bounds, there's going to be a plus c at the end. If there are bounds, then we don't have to worry about this. So this is the general form of any integral that has some coefficient a in front and and then some constant b added onto it. It's just 1 over a multiplied by l and absolute value of ax plus b. Now it'll be slightly different if x had something over there, but it's not as common, and so we don't need to go into that right now. And it's not integral to our problem. And then we do the same thing for this part over here, negative 1 half. We're just leaving out the coefficient. We don't need to worry about that. And then we take the integral of u plus 1, 1 over u plus 1, which is just the natural log of the absolute value of u plus 1. And then just writing these things down as aforementioned to remember to plug that back in. But because we didn't plug these things into u, we got to go replace the u's with what we substituted out, the original x terms. Or otherwise, we could just plug the bounds into the equation for that and then get a new bounds and then plug that in straight into u. But slightly more complicated in this case, as the equation we're dealing with is going to be quite long in our bounds. So let's just replace the u's. Okay, and now we have done this, then we can go begin the long business of plugging back all the a's and zeros backs into our equation. Technically, we can clean things up a little bit first. And what we're going to do is we're just going to take these natural logs and we're going to combine them together using the rule that the natural log of some variable a subtracted from the natural log of some variable b is equal to the natural log of a over b. It just makes things nicer and easier to deal with, and also shorter. So I'm just going to rewrite this. And then we can factor out a 1/2 as both of the ln's, the natural logs, have that. And then the absolute value of 1 plus e to the 2x negative 1 all over the square root of 1 plus e to the 2x plus 1. And then the other absolute value, and then a and 0. So now we begin the arduous process of plugging in the a's and the zeros, but we're almost there. So now we're just solving out the integral, and so we plug in a into x for this first part, 1 plus e to the 2a, and then we subtract that from the second bound, which is 0. We plug 0 into x, so 1 plus e to the 2 multiplied by 0 is just 0. So in reality, this is just 1 plus e to the 0 is just 1, so it's 1 plus 1. And then 1 plus 1 is 2. So the square root of 2. And then we move on to the next part, this chunk over here. And then we just keep the addition and the 1/2 as is. And then ln of plugging in a into the x's. So 1 plus e to the 2a, negative 1, all over square root of 1 plus e to the 2a plus 1. And then now we have to subtract the 0th term. So subtract that from ln, natural log, of the absolute value of, well, e to the 2 multiplied by 0 is just 0. So everything here, once we replace the e with the 0, is just 2, because it's just 1 plus 1. To the 0 is 1. So we just have square root of 2 negative 1 all over the square root of 2 plus 1, absolute value, and all this is multiplied by 1/2. And all essence, this is our final answer. Of course, we can clean things up to make it a bit nicer, but an answer like this would work just fine.